Well, welcome to this policy forum, this Google and New America Policy Forum here at the Googleplex, Pervasive Connectivity, Open Airwaves, Open Networks. My name is Michael Calabrese. I direct the Wireless Future program at the New America Foundation, which is a nonprofit, very nonpartisan think tank in Washington, D.C. The chairman of our board happens to be Eric Schmidt, the CEO of Google, who was one of our founding directors. And, I just very much like to thank Andrew McLaughlin for inviting us to hold this very well-timed event here at Google, and thank Derek Slater from the wireless team for doing the organizational work, and Marseille Steele for doing all the logistics and keeping us on track. And thanks to all of you for battling your way through whatever traffic you faced up and down the peninsula to get here. So we'll have three panels in turn on three issues that we see as really being very, very connected to each other, and that is open airwaves, open networks, and community networking. In particular, its relation to digital inclusion. And it's really a happy coincidence that we're holding the event here this week, because we're at a potentially historic moment for wireless broadband and communications policy. Last week, FCC Chairman Kevin Martin announced an order opening that would open the vacant TV channels in each local market to unlicensed sharing. And it's now on the open meeting agenda at the FCC for November 4th, an amazing thing that they're trying to pull off, which is to have a huge consequential meeting on Election Day. I think it may be Kevin Martin's way of trying to thinking he's not quite yet a lame duck until the polls close. So in any event, reallocating this beachfront spectrum from broadcasting to broadband has been part of really a 6-year struggle, something that should not have taken that long, but hopefully we're in the last lap. When New America first proposed this back in 2002, most Washington insiders said that you will never ever be able to pry tens of billions of dollars worth of airwaves, except perhaps from the dead grasp, of what was perhaps the most powerful lobby in Washington. But we've had this huge coalition of public interest groups, consumer education, civil rights, and of high-tech companies led by Google and Microsoft in particular. And indeed, we haven't quite gotten the job yet done, and so we're going to need all of your help to encourage the FCC to serve the public interest on November 4th and get that done. However, the issue of white space and access to the airwaves is actually a much broader one, of which the TV band is just the beginning. And so to start this first panel, that's what I'll take a step back and talk about. To start, just to let you know who we are. New America, as I said, is a think tank. Our mission, pervasive connectivity, and our means, openness, particularly open airwaves, open networks, open technologies. Now, what's interesting is one of the things that we're up against in Washington, the land of Congress wanting money from auctions, is the conventional wisdom that spectrum is scarce. And in fact, if you look at the U.S. government map of the airwaves, it certainly has all been assigned to someone. But the reality is that what's scarce are spectrum licenses. This is from our Citizen's Guide to the Airwaves. So government permission to use the airwaves is certainly scarce, but the reality is also that spectrum bandwidth is abundant. In other words, 90% of the airwaves at any given time, even in major cities like New York, as you see there, and Chicago, even around Silicon Valley and over downtown D.C., are not in use. This is actually a summary measurement that Mark McHenry did in a study for the National Science Foundation, which I think you'll hear more about. Now, who has all this white space? Well, most white space, which you can think of as being wasted bandwidth, is reserved for federal government use. And there's Uncle Sam, pointing to a big chunk of it from our Citizens Guide. So here's some examples of spectrum allocated for use by federal users. In particular, notice those two yellow bands. That's 275 megahertz of spectrum, more than the cell phone industry has, which is basically used. I don't know if you saw back, but you'll see again in the next slide. Here, it's kind of hard to read, but those two bands, about 3% at most, is in use certainly around major metropolitan areas. Basically, this is military, air and satellite spectrum, which is used for very important purposes, but mainly around Air Force bases, satellites, high up in the air. There's certainly we can find ways to share some of that, and also many of the other federal bands, because the federal government is by far the largest occupant of the airwaves. The other largest occupant of the prime beachfront frequencies is television, because when they came along in the 1940s and 50s, there wasn't much demand for the airwaves, and the technologies were such that only the lowest frequencies could be used. So below 1 gigahertz, the real sweet frequencies that penetrate through buildings and trees that fetched $20 billion at the auctions early this year for just, 10 channels, is 40% of that is reserved for television. But as you can see here, it's not the 1960s, and we sometimes have to think about different ways of using this precious natural resource, particularly when we're down to about 10% of households that are watching television over the air, and the DTV transition could push that even lower. So you really have the very best airwaves that are being used by fewer and fewer people all the time. So there are many ways to increase access to this valuable bandwidth. So think of here we are with 90% of this resource, an infinitely renewable resource from millisecond to millisecond. So frequencies can be white, and thus they can be shared on a number of different dimensions. Geography, that's the TV band. It's not in use everywhere. Time, not continuously. Spatially, in the air and not on the ground. And even angle of reception. So when satellite receivers are pointed south for the bird over the equator, you can receive signals the other direction. So there are two very general ways in which the sharing can occur. One, and both of them are kind of ongoing right now. One you might think of as underlay. That is sharing underutilized frequency bands. An example is the way right now Wi-Fi has just begun sharing a large portion of the 5 gigahertz band with military radar using listen before talk. In other words, it senses. If it hears something like military radar, it gets off that channel in under a second. If it doesn't, which is most of the time, it can use it. The other is overlay, filling unoccupied frequencies. And that's the example there, again, is the TV white space, because these frequencies aren't used in every market. Here again is a measurement Mark took from our roof over the White House in Washington, and you see, like that other slide, and you see here we focus in that between channels 8 and 14, 5 are empty. But here's the TV white space dilemma: is a lot of spectrum in recent years, if it was very lightly used, it's been cleared and then auctioned. Because and that's what happened recently with the 700 megahertz auctions, channels 52 to 69, because we were able to get broadcasters off there entirely. But for the rest of the TV band under channels 52, it's really spectrum Swiss cheese. For as long as DTV remains on the air, there's a different pattern of channels available in each of the 210 local TV markets. So you can't really aggregate the spectrum consistently, because you also have to protect, television viewers. And TV receivers are like eggshell receivers, very sensitive to interference. So these are reasons that it's difficult to use the spectrum, particularly for higher power or licensed use. Relatively low power limits. The FCC has proposed 4 watts, up to 4 watts in rural areas. Although this is more powerful than Wi-Fi, and it's great for rural broadband, it can only be used where there's 3 empty channels in a row. The FCC is saying we'll only let you use the middle of 3 empty channels because you can't be operating right next to a TV station. And where you are using adjacent channels, 40 milliwatts, which is actually lower power than a home Wi-Fi router. So how can we make good use of this white space? Well, this is where you have cognitive radio to the rescue. The majority of TV white space channels that are not usable above 1 watt of power become usable on an opportunistic, license-exempt basis if, first of all, you're low power, under 100 milliwatts. Now, the FCC is proposing 40, and we're going to try to push that up over time. But then very important as well is that the radios are cognitive. Like the sharing of military radar at 5 gigahertz, they need to be able to detect where TV is in operation and avoid it, either through a geolocation database, in other words, the devices have GPS, or through the listen before talk sensing. This results in spectrum efficiency, more than twice the bandwidth is usable, national availability. As you'll see, the big markets won't be blocked off. So you have national equipment markets, open access for consumers and innovators, regulatory and business model diversity. And so we really see the TV white space as a test case for opportunistic access to underutilized government and even commercial bands. And here's why one reason it's important to make this unlicensed, because while there's something like 600 million devices, unlicensed devices operating in the Wi-Fi, so-called Wi-Fi band at 2.4 gigahertz, there's really not a good, enough of a varied ecosystem of unlicensed spectrum. So you can see, how there's so many more times the amount of spectrum of flexibly licensed spectrum available compared to unlicensed. Below 3 gigahertz, it's really limited to the Wi-Fi band and 900 megahertz. So the TV band is great because at low power, there are between 7 and 40 channels across the nation's 210 local TV markets, ranging from around 18% availability in the TV band in New York City, the worst, to 60% Wichita, Kansas, and even more in places like Montana, Alaska, and so on. So we've been fighting a battle against those who would like to auction, who think, no, Coase, some decades ago, right? Coase theorem, Coase said the most efficient way to use anything is to create property rights and auction it. And so the trouble, though, with auctions here is this 40 milliwatt power limit suggests that the adjacent channels, which are most of the white space channels, you won't be able to use those. So if you do not use the channels on either side of an occupied TV channel or the same frequency, the co-channel in the neighboring markets, what happens is most of the white space goes away. And similarly, if you eliminate the lower VHF channels, as the cable industry is insisting and the FCC is doing because of other forms of interference, it's also not very useful for mobile consumer applications. So Washington, this is the same slide you saw, Washington, D.C., there were 5 channels in the upper VHF. Suddenly, there's only 1 left, channel 12, because the others at more than 100 milliwatts, they go away. They remain guard bands, if you went with a licensing model. New York City and Dallas have respectively 7 and 13 channels, so each one is 6 megahertz, right? So, do the math, that's quite a lot of spectrum. Remember, only, I think about 50 megahertz was auctioned for $20 billion earlier this year. 7 is 42 or 78 megahertz respectively at low power. But if it was higher power, in other words, if you licensed and auctioned, you'd have to protect adjacent channels. New York City goes from 7 available channels to 0 in a licensing model. Dallas goes from 13 to 1, but then if you protect that one channel, channel 23, I believe, is co-channel to 2 other markets, you have 0 spectrum available in Dallas on a licensing basis. Detroit, similarly, 17 channels for broadband, which they could really use there. It goes down to 4 when you protect for interference on for a higher power use, and there's only 1 left after you protect for cable pickup, the low VHF. So from 34% available white space to 2%. So all that's to say that the low power unlicensed use really, gets the juice out of the spectrum. 2 myths that I'll just mention about auctioning, white space spectrum, which is important too because, as I said, we're hoping, and in fact, that that these debates are going to come around again, even if the FCC acts affirmatively in 2 weeks. One is that this will generate $10 to $20 billion. There's a paper which you could pick up on, during a break on the way out in the back there, where we get into debunking all of these. So there's some papers to pick up on the back table. Looks like this, but where we kind of go into all the math. But essentially, it's the notion, as I just said, that this is really not very valuable for licensed use. First, because most of it will remain guard band. There's virtually no availability in the large metro markets. The white space spectrum is also unpaired, narrow channeled, and still relatively low power where it is available. And you compare that, for example, to the license models out there. The people willing to pay big bucks for spectrum are operating minimally at WiMAX 2,000 watts, or Qualcomm's MediaFlow, which operates on channel 55 after the DTV transition. They bought that at auction, 50,000 watts. It's a broadcast service. Even WiMAX is a type of broadcasting, in a sense, a cellular kind of architecture. Even 4 watts in the non-adjacent channels in the rural areas is nothing compared to the business models for licensing. There would also still remain interference from 500,000 wireless microphones on the TV white space, which unlicensed devices can live with, and a licensee maybe not. Those who've made these projections also try to compare it to the auctions that were held earlier this year. I mentioned that raised $20 billion. Not a good comparison. Those channels were cleared nationally. They were paired and teed up perfectly for the business models of the existing wireless carriers, which is why Verizon and AT&T bought 80% of those airwaves. The other myth is that licensing reduces the risk of interference. There's no reason to believe that these low power limits to protect television viewing would be relaxed if suddenly the FCC decided to issue licenses. And the suggestion that licensees could bribe the TV stations to cut off their viewing audience it's just seriously argued by the cell phone industry and by Qualcomm, is unrealistic. They have a statutory obligation. That's why they got their spectrum free, to provide free television. Again, winding down now is just to, which helps tee up these next 2 speakers, is this idea, the cognitive radio. We can do more with it. So the FCC is proposing a very conservative first start, but this was actually a study that Paul Colazzi conceptualized for us at the Spectrum Labs at the University of Kansas, a bunch of former DARPA engineers. And what they found out, here's a situation where you have actually two DTV channels that are operating adjacent to each other, okay, which they can do as long as they're, one doesn't overwhelm the other. And you can put in a white space device operating at 100 milliwatts, for example, can operate immediately adjacent to them using transmit power control. If you power up or power down, depending how strong you sense the neighboring TV signal. And the FCC currently isn't allowing for that, but we're hoping to move them in that direction. So this all just suggests, again, that with cognitive radio, we can do so much more in terms of sharing the empty white space across the spectrum. You just need rules of the road, like public highways and ocean shipping lanes. Exclusive licenses are inefficient for low-power uses in particular. The high transaction costs, you miss the economies, the public goods economies, and so on. And so finally, to conclude, the future, we believe, is opportunistic access to the airwaves. Let smart radios operate around the dinosaurs. Politically, it's going to be very difficult to get some of these old users, there's still a lot of analog users, television, and so on, off the air. But if we can first clarify license rights, open unused spectrum for non-interfering use, millisecond to millisecond, because it's a public resource, it's being wasted, and look at market-based carrots. Maybe it'll take making micropayments or micro-auction payments to federal agencies that hold the spectrum or to commercial licensees. And it's also a good congestion pricing can also be a safeguard against a so-called tragedy, the commons from unlicensed, an argument made, but so far has not been a problem with Wi-Fi. And then finally, take TV off the air. I think now that we have, hopefully we'll have the white space, it's time to realize that that television needs to, transition to be completely, cable, DBS, and over the internet, and then we can use the entire TV band in a much more robust manner for wireless broadband. So with that, I will turn it over to for presentations to Paul Colazzi first, and then Mark McHenry. Paul is, of course, the head of Colazzi Consulting, not his dad. It's you. Colazzi Consulting. He's a senior technology advisor to M2Z Networks, and in the past has directed the Center for Wireless Networks Security at the Stevens Institute of Technology. Kind of in some ways most notably for this, he directed the Spectrum Policy Task Force at the FCC in 2002 under Chairman Powell, where he came from DARPA to do that and really educated I give him credit for totally turning around Chairman Powell on the whole issue of the value of dynamic spectrum sharing and unlicensed, and that led directly to the TV white space proceeding, and he was at DARPA before that, really getting the military on the road to these technologies long before they were talked about in the public sector. Paul?
Okay, thanks, Michael. Just to give you a little bit of a time frame, and when the first slides come up here, I'm going to talk about DISPAN. You're going to try to ask the question, what does DISPAN mean? DISPAN stands for Dynamic Spectrum Access Networks. And there's a lot of synonyms or a lot of phrases that go along for opportunistic spectrum. One of them is called Dynamic Spectrum Access, Opportunistic Spectrum, Dynamic Spectrum Access Networks, DISPAN. These are all kind of terms that are actually kind of used ubiquitously and interchangeably with each other. We just came from a conference called DISPAN 2008, which is the third conference that actually focuses on technology and policy issues for opportunistic and dynamic spectrum access. So a little bit of a plug. That's sort of where a lot of the action is happening, where people are actually discussing what is the next steps here, both in the policy domain and as well as in the technology domain. When you try to talk about opportunistic spectrum, what you're actually asking about right now is, number one, is there spectrum out there to use? And starting around 1999, actually starting initially with some Mark McHenry measurements when he was at DARPA, basically started showing is that if you start looking at time, space, and frequency, things look very differently. There's a lot more spectrum out there to be used than was expected. And the reason is because you just kind of looked at it in a very different way. By 2002, DARPA had eventually started a program to go off and do that called the XG Program, which Mark will talk more about later. And actually within the last few years, actually within the last few months, actually has completed that activity and is transitioning it right now into the DoD and alike. The commercial world did a little differently. The commercial world then went to the FCC and tried to get these proceedings going. So now we're just starting to get, now about the same time, dynamic spectrum hitting with TV white spaces. What I'm going to try to tell you is that's not the only place for opportunistic spectrum. There's a lot of areas out there, and we should actually be thinking about opening up our minds as to what is possible and then how to actually get from here to there. So what's the big deal? The big deal is that we all want to try to get internet access, and we have to worry about this thing called the trade-off between providing access and providing this density. This is an OECD set of data that actually kind of shows that it's not quite correlated. It used to be the argument that, hey, you only get lots of access where there's lots of high population densities. This tends to blow right through that because the red line is the population density, and you can see some very, very high numbers even with very low population densities. And what's happening in this world with all of this work, trying to go this technology development is that you're seeing a rapid change with this, the cognitive radios, this SDR technology, and basically people are getting very ingenious in actually how to access the spectrum. And that we do this a lot in dice band and the like. They basically have one basic problem. That is the policies that actually are out there to be able to access the spectrum kind of not getting up to speed with exactly what's going on with their ability to access the spectrum. And there's two ways you can actually think about that. One is, Michael was talking a little bit about the opportunistic spectrum side. There's also the secondary market side, which is that when people actually can have licenses and actually try to share the spectrum and put them out in the marketplace, either for opportunistic from unlicensed use or for licensed use. But the problem is that the technology for this is a very, very, it's not complex, but it is different. And therefore, there's an education process that's going on right now between the policy world and the technology world. And actually, I think I'm glad that we're all kind of getting together here because I think you have a mix of those groups here together today. Where's the action right now for opportunistic spectrum, or in some sense I consider dynamic spectrum? And that here I just show you some of the areas. Some people say the whole spectrum is open, but we have TV white spaces that's going on in this area. Upper 700 megahertz, which just auction, actually has some issues that are trying to associate themselves with dynamic spectrum, or dynamic spectrum can actually help solve some of those problems. AWS-3 has been going on looking at possibilities of where there's interference issues. Can you actually solve it with dynamic spectrum? BRS, which is the 2.5 gigahertz band. UNII, which Michael talked a little bit about, which is the 5 gigahertz that was opened up, which was sharing with the federal spectrum. That was the radar folks that are actually operating in that spectrum. And then the 3.5 gigahertz. There's a lot of spectrum out there that's been going on here, so it's not just a TV white space. This technology is much more ubiquitous than you think. And I'll try to give you an idea why and how. Here's the basic dimensions of DSA. What I told you before is that DSA is trying to do a trade-off between frequency and changing in frequencies, changing what happens in different spatial areas, and what's happening in time. And it's really the combination of those three that you're trying to take advantage of, not one or the other, but all three. And if you take a look at that, how do you apply that? Well, you apply that type of analysis into either how to access the spectrum, which is what we're going to talk mostly about now, but also interference avoidance, which allows you to access spectrum more freely. One of the basic issues is that if you don't use all those dimensions, you have interference possibilities. If you can actually start using those to tease apart the interference, spectrum that was thought of not being available now becomes available. And so now you start opening your minds up into new ideas, and that actually comes down to coexistence. One of the areas that's a big problem is how do you get coexistence, meaning there are different types of ways of accessing the airways, right? There's FDD, which is generally cellular, and there's TDD, which is like your Wi-Fi node. How do you get those two to actually coexist and be able to interoperate together? DSA actually provides abilities looking at each one of those, and I'll try to give you some examples. Mark will go into great depth, and Michael already did, as doing the spectrum access for active spectrum users, meaning people who actually want to send and do communications. But another area which might be of interest, which you may not think about, is in the passive domain. Is that you actually have folks that are actually doing Earth exploratory satellite systems, okay, surveillances, which is down-looking. They want to use a lot of different bands, but they don't have access to all those bands. But they're also not in the same place at any one time. They only stay in a certain place for a few minutes as their satellites are rotating the Earth. So is there a way of actually using dynamic spectrum? You're changing what frequencies you're looking at, changing it where you are looking at that, at what time and what position. And Kepler laws, which means you had to know where the satellites are going at any one time, allows you now to actually understand exactly when this is going to occur. And maybe there's some synergies that can go on with Earth systems that might cause interference with the satellite systems that are trying to make measurements, and vice versa. So there's an idea here that's going on. I've been a study. There's actually 2 national studies that are going on right now in trying to understand new ideas in spectrum access. One of them is for the scientific community that I'm on, and another one is actually looking at technology for spectrum policy, and that's another one that's going on with the National Academy of Sciences. Another area that you can think about and how to use this, and I'm sorry, it's the geeky slides here. Sorry for the geeky slides. This geeky slide, what you're supposed to get out of it is that if you have lots of spectrum and you can change your bands, you no longer have to make such an expensive radio. Because if the radio kind of knows how it's going to, what kind of like pollution it's going to have, how big its shoulders are, then if you know that and you know how sensitive other receivers are, you can actually move around them to prevent interference from occurring. So you could actually start thinking about making actually lesser expensive devices and the like. And that's some work that's going on right now by actually another colleague of Mark's and mine at DARPA, who is now actually trying to get his PhD from Trinity College. And he's actually been able to show that he's able to really reduce the requirements on radio development by actually using dynamic spectrum. And what he's trying to do there is there's this program called the Wireless Networks After Next, and we'll test you on all the little dots here in a few minutes. But what it really comes down to is that you could make a very inexpensive radio, okay, for the military. Now, military radios, if you don't know, run between $5,000 and $150,000. They're trying to build a radio for $500. And the whole thing is based upon, if I can use dynamic spectrum, I'm able to actually find places where I can operate cleanly with a less expensive radio. I try to get away from the interference. So instead of trying to find the open holes, I'm now trying to find the less interfered areas. Okay? A little bit different way of thinking about it. Same concept, just a little different implementation. And in coexistence area, okay, one of the big areas in coexistence is mobile-to-mobile interference. If a mobile is transmitting next to a mobile receiving and they're near each other in frequency, the question becomes, okay, that one could interfere with the other. The one that's receiving could be interfered with the one that's transmitting. How do you actually make those two coexist? That's important, especially if you want to open up all these airways, because you're going to want to actually take your opportunistic spectrum and shove a transmission right next to somebody else, right? That's the whole idea of using opportunistic spectrum. Well, how do you actually deal with that coexistence? And is there a way to do that, okay, in a statistical manner? And the answer is that, as I show here in the slide, is that if you have that TDD, okay, which actually is transmitting and receiving. So TDD, for those who don't know, is time division duplexing. So it's like your Wi-Fi card. So that basically, it transmits and receives on the same frequency. It goes, hello, thank you for talking to me. Here's something else. Okay, I'm listening. That's TDD. FDD is, I talk to you on this frequency, but I listen to you on that frequency, okay? So on this idea here is that if you're listening on one frequency and somebody is transmitting and receiving on a frequency right next to you, that can cause problems. So the question is, how do you solve that problem? And the answer becomes that, well, the problem actually is not just in one band or the other, but it's all around the spectrum, okay? And this is an international possibility. This is the bands. In fact, some of the things I'm talking about here is actually going on in the EU right now in the 2.5 gigahertz band. It's happening here in the United States. The idea is how do you actually prevent and provide a coexistence structure? Because if you want to open up all these bands, and that's the reason, by the way, the FCC is not, does not think about these problems just casually. They actually try to build their band plans up very carefully to make sure that everybody lines up appropriately so there's no chances of possible interference. And they put guard bands in. They put these large empty holes of spectrum in. Why? They don't do that just because they don't want to use the spectrum. They do that because they don't know how to use technology. They don't think there's a technology that allows these guys to coexist. But if you can actually have a technology that allows them to coexist, now all those empty holes of the spectrum now become available. And so the question is, how do you do that? And so one simple example is, remember, it's time, space, frequency. Everything has to align. So if you have two cell phones that are next to each other and they're interfering with each other because one is using one frequency and the other one is using one that's right next to it or the same frequency, well, if you have another band to go to, if you jumped so that the two ones that are close to each other, so if you're close in space, use different frequencies. If you're far away in space, use the same frequencies. It's almost like using a cellular concept, which is what cellular does. They reuse spectrum by using cell sites, but now you're using it in a very fine granular way right directly on devices. And so now it opens up a whole area, again, of new ways of thinking about the problem. But the policy issue now becomes, And that's where this transition goes with what the federal government has to do, and that's what Julie was trying to do, and the commissioners are trying to do now with the TV white spaces, is what level of interference is considered to be okay. First of all, every device has interference. What is the level that's okay? Is it all the way down? I suppose the thing called KTB. That's actually the noise floor. Okay, that means that thermal noise is that level, no matter if you do nothing. And there's a practical noise floor. There's an interference floor. Or you're allowed to accept so much capacity loss. That's the policy question. That's the issues that the policymakers have to do. Is where's the line? Where do you consider that somebody's encroaching on somebody else, okay? And the answer has been, for a long time, and I think that one of New America has been arguing about, it's not KTB, it's not the practical noise floor, but it's someplace a little bit above that because there's a place where you can coexist. We don't work in what's called a noise-limited environment. We work in an interference-limited environment. Everything interferes with each other just a little bit. The question is that can you actually build a system that actually can be tolerant of that? And cell systems are tolerant of that. So what are the next steps for this community to actually start thinking about? Number one is that, just to remind you, is that technology, policy issues, and economic issues, if you can build it, but you can't use it because the FCC won't let you use it. If the FCC will let you use it, but you can't afford to build it so you can make money, then you don't have a winning structure. So you need to basically intertwine those and understand all three of those areas. There are lots of opportunities in the RF spectrum. It's not just TV white spaces. So TV white spaces are going to be at the forefront of actually showing this technology can actually work. And look at how you do interference analysis. And I think there's a lot of opportunity out there to actually develop the technology to allow other places of the spectrum to be opening up because it has actually addressed the interference issues. And with that,
thanks, Paul. We'll bring up Mark McHenry, who is the CEO and founder of Shared Spectrum, which is a company actually trying to make a business out of this new frontier. Mark, like Paul, had been at DARPA at the very beginning of the Next Generation Spectrum program. He's also a co-founder of the San Diego Research Center, and I really want to thank Mark and his colleagues for bringing this demo all the way from the East Coast. It's in the back of the room. At the end of this, on the way down to lunch, everyone should take a look. It's essentially, well, you can describe what you think they'll get out of it, but it's very cool.
Well, I guess I was here to bring you guys up to date on what's real, because this all seems like view graph engineering, and when is this all going to really happen, and how to make the view graphs go. Well, it turns out this is very real. In 2000, I was at DARPA, and when I left DARPA, in 2002, this XG program started. And we were the winners of all the contracts. So I'm going to give you kind of an overview of the XG DSAs. And the conclusion is this is all very proven technology, and we do have prototype radios right in the back. So this is kind of the outline of the talk, a little bit about what XG was, and then we'll spend a little bit on what DSA really is. Then we've done a lot of field testing. I've been in airplanes, we've been in ships. We've tested this extensively for DoD. So I'm going to give a summary of those field tests and then some conclusions. Shared Spectrum Company, obviously this is our main product area, and we believe we're the leading company in this because of all this DARPA work. There's a list of big companies here. We're putting our software into their DoD radios. There's some handheld, I'll show you some pictures of these radios. And then we're teaming with these other people to go forward. We're talking the JTRS program. This is the main program of the Army, of the whole military, to put it in their radio. So what is this DSA? You've kind of heard what it is. It's software in the radio that finds spectrum that's not being used. And the rest of this chart lists a bunch of benefits. And when we started, it was kind of this benefit down the bottom. Oh, we're going to go to someone else's spectrum and borrow it. And for a couple of years, that was the emphasis for DSA, is kind of go out of band and take someone else's spectrum. But what DoD figured out very quickly is these other benefits were really, really important to them. I mean, we have one customer now who's flying airplanes, and when you fly airplanes with an air-to-ground link, it doesn't take much co-channel interference, and your link is dead. And so what they really care about is reliability and availability. And there's a lot of, there's high co-site environment. I can't say the J word, but there's very tough electromagnetic environments that DoD operates in. So this radio, DSA, allows it to, if your buddy jams you by mistake or the bad guys jam you, whatever happens, it just relentlessly finds a channel that works. And then Paul already mentioned the hardware costs. We're talking a huge reduction in hardware costs. This JTRS radio is over $100,000 because 1% of the time it's co-site with somebody else's high-power expensive radio. But 100% of the time they have to drag all this hardware with them. So when that 1% happens, you just go to another channel. This has now become the overall, DARPA is just really focused on saving money and build cheap radio. They don't even care about all these other benefits compared to the reducing the costs. Another big value of this is it can pick the best frequency. The radio automatically finds a frequency that closes a link. And NIST and other people have done studies. If you wanted to send a signal into this building, who knows what frequency would be best? And I guarantee you the best frequency to the worst is a 30 dB advantage. It's a huge amount. If you come see me afterwards, I'll give you the NIST websites where they actually made these measurements. They got spectrum network analyzers and swept all the channels. So this improvement in link range is a big deal. And then what the DoD now wants to do is pooling. If they could just better manage the spectrum they have now by pooling versus this command and control thing, that's of high value. So the DoD, and I'll talk about later, has really jumped in on this. And the thing that the white space thing is kind of in the noise to them at this point. They don't need that right now. So the DARPA XG program, it started in about 2002. And the first thing that happened is the DARPA director did not believe there was unused spectrum. Why are all these spectrum yelling matches? It must be totally full. So he forced us to go out and make spectrum measurements. And then we subsequently we had NSF projects. And they're all on our website. If you go to our website, we made all the results public. The spectrum is totally empty. If you would take broadcast out of the mix, it's a few percent. Even on an elevated building in New York City, it's maybe 10% used. So all this arguing, that huge spectrum chart, it isn't, quote, real. It's not fundamental. It's just an access question. So over the last few years, up till 2008, we took on the big companies and beat them, and we developed the technology. And unfortunately, it's over. We'd like DoD to fund forever, but DARPA has this thing, tough love. After 4 or 5 years, if the Army doesn't pick it up, it must be a bad idea, and so they just stop. So, but the Army is picking it up. So we're working on that, and so this is kind of the history of DSA. I think this XG program really was the genesis of DSA. It was talked about and so forth up to that point, but we made these measurements. And when we started, there was no idea how to do this. It was unclear what algorithms they need, what hardware was needed. It was a lot of, I would say, fumbling around until we finally figured out what was involved. And we built the software and the hardware. These are 2 military radios that are fielded in huge numbers in Afghanistan and Iraq. And we put our software into those radios. And what it allows them to do is it greatly increases their link range in challenging situations. It's not in Iraq yet. But I mean, it's a software upgrade. We could just ship a CD, and they could upgrade those radios immediately. And this is our fancy radio here, which is 802.16 base. We have smaller versions in the back there. But this is a radio designed from the ground up to do dynamic spectrum access. It's got special detectors and very agile transceivers and so forth. This is just a little quick summary of what DSA software architecture is. At the top, there's all these policies. And right now, when the FCC makes a rule, they kind of have a sheet of paper with a very simple rule, and everyone has to build to it. We think it's going to be very dynamic. The rules will be represented in a high-level language. They'll be downloaded to the radios. The FCC is going to change their mind, and you go to Japan, there'll be another set of rules. It's going to, because you have to deal with a Swiss cheese, the rules will be complicated. So there's a whole policy part of this inside the radio. There's detectors in the radio. There's the way you talk to the radio. Kind of a hard thing of DSA is when you transmit or receive, you can't be sensing. So you have to tell the radio to quit what you're doing. I need my turn to sense. So there's parts in there. And then there's a lot of rendezvous and frequency negotiation. If everyone ran DSA, how would you connect to other people? You have to be able to search the spectrum and find other people. This is more details of our radio. When we started, we thought, oh, we'll just make a radio cover DC to daylight. Wouldn't that be cool? We could jump around and go to anywhere in the spectrum, but we found it was too expensive. So we ended up making separate RF cards to cover different customer spaces. We have DOD space, public safety, the TV band, and this is all the spectrum that's been auctioned. And right now, DSA is legal. We can go right to the deploy it in the DOD band. All I need is 2 or 3, I call them spectrum weenies in DOD, but the burden to get into the DOD space is very, very low. And there is no burden in the Secondary Markets Initiative. Paul and Chairman Powell said if with the spectrum that was auctioned, they can do whatever they feel like. And of course, the place the DSA is getting rolled out first has the biggest hurdles, which is the TV ban. That was unfortunate. In the public safety, there's some regulatory hurdles. But to first order, half the spectrum is totally open to DSA, and we can come charging right in. These are another pictures of the radios. We've been focusing on people that were just dying for spectrum problems, and this is a UAV radio, 1 pound radio. We also have made this back there. So testing. That's all I've done the last 3-4 years. Really, the DSA development, the hard technology stopped in about 2006. It was all, we had a shopping cart radio. It was a huge 100-pound radio back in 2006. The emphasis was, can I get the cost down to something that's cheap, and can I really show it works? And so we reduced the size way down, which you'll see in the back there, and then we did a huge amount of field testing. Here, this is a military radio in a van, and we drove by pairs of our DSA radios in 2006, showing we didn't cause interference. We've been out on ships doing very long over-water links, and we just completed some airborne tests. So we've done land, sea, and air. We've tested and tested and tested for the DoD. And now we're selling our radios to various DoD groups as development kits for them to really put it in their lab and beat it to death. So we're kind of like on the final stage of DoD acceptance where the individual labs are buying the equipment and trying it. And this is just more details of what the DoD is doing. The Secretary of Defense's office likes it. The House Armed Services Committee, if you dig through the testimony, they've said this is the way forward for DoD to fix their spectrum problem. And we've already heard about this wireless networking after next project. This is a huge change in direction for DoD to build these cheap radios at low cost. NTIA is starting another effort that parallels the white space called the test bed. They put spectrum aside. There's been 6 companies, and this is kind of I would say a stealth test. It's not as public as the white space, but it's very important because they're taking the radios and in the lab at Boulder are going to do these tests. And what we're focusing in a lot on is the radios, but there's a lot of networking aspects and how do you manage this and how do you migrate from what they have now to this. It turns out to be a very big, rich area for DoD to invest in. So there's a lot of interest in white space and shared spectrum. We didn't participate in the white space because we were focused on DoD. But it turns out a year ago we actually did a fairly large field test program to show white space works, and we published a paper at DISBAN, our first rollout of these tests, and I think we're submitting it to the FCC today or tomorrow. What we did is we took pairs of DSA nodes. One was a base station and one was inside, and we went to many different locations in the Virginia area and collected data. The question is there a sensing threshold where you make the right decision? If you have this is a percent time and this is threshold. I know this is really technical, but this is kind of the fundamental argument behind this white space thing. If you put the threshold too high, it'll turn on inside the gray B contour and cause interference. If you make it too low, it'll false alarm and you'll never get any spectrum. So this is, red means cause interference and blue means false alarm. And then we drew curves here where we have a low false alarm rate and cause no interference. I think we fundamentally proved, at least in these scenarios, that it worked. So, I mean, there's very little technical doubt that the white space is going to work. We've tested it to death. You'll see our radios back here are sending video while we're hopping around, and we show it's not too complicated. We show the physics are there for interference avoidance. So it's just a matter of time. And the FCC is going to start very conservative, but we're going to wear them down. And within a few years, we're going to be out there 10 watts all over the place because it works. And the FCC, we've had a lot of discussions with the FCC. They're amenable to this. You just have to show them in detail. And so we're beginning to roll out our data to them. So our strategy is, we've got an IP situation, but we've been focused totally on DoD and these people that are dying for spectrum, either spectrum or robustness. And that's how we're rolling this out. And eventually, I think this is going to be every radio you buy. I can't imagine a radio in the future that won't have DSA in it. It's going to take a while, but there's definitely a migration path from DoD to public safety, kind of rolling it out. So in conclusion, this isn't just a concept. There's just not a bunch of view graphs that Paul made up. There's been a huge DoD effort. I mean, tens of millions of dollars being spent and a lot of testing. And the government's getting interested enough that they've set this whole testbed situation or project up where you have to give the radio to, just like the FCC did, but it's being done by Boulder. So, I mean, the government, NTIA is getting very involved. And like Paul said, the white space is just the tip of the iceberg. I think it's a shame that's where it started, at least publicly, because they had such a big enemy there, the broadcasters. But I think that one of the themes of this conference was pervasive connectivity. DSA is going to get rid of, there is no spectrum shortage. When we started laying out tests for DARPA, we couldn't afford enough radios to fill the spectrum. We'd have to, 6 or 7 radios, 6 channels, that was our test. You can't put enough radios in an area to truly fill it. So the whole spectrum scarcity thing is going to go away in the next few years. And then the performance of radios and link range and robustness and cost, it's going to make a huge difference. And in the end, the economics of wireless is going to totally change. Equipment costs are going to go down, link range is going to go up. It's going to make a huge difference to wireless in general. So I welcome you to see our demo in the back when you leave.
I guess we could jump probably straight to questions and comments from the audience and do it from here, because I know a lot of this was technical, and I don't know if if everyone quite appreciated some of the connections between what I was talking about and as a lawyer, my simple-minded Washington policy speak and these DARPA gurus, but this really was a way, I think, of just showing that what we've begun to do as precedent in the TV white space really has this enormous implication to eliminate spectrum scarcity and thus the control of certain incumbent licensees over wireless and to do it more efficiently. So,
yeah.
Pardon?
Yeah.
Oh yeah, I think somebody's walking around. Oh yeah, go to the mic. And let us know who you are and where
I'm
you
nobody.
Don't believe her.
Because we're capturing this audio.
My name is Helen Mickiewicz, and I'm an assistant general counsel at the California Public Utilities Commission, and we don't have anything to do with any of this stuff in a technical sense. But I'm asking this question, Michael, of you for a couple of reasons. One is that I'm one of the dinosaurs. I'm the 10% of the population who does not take cable or satellite, and I rely exclusively on gas broadcast. I actually have a background in some broadcasting many years ago, but now I do telecom. And I'm also asking this question because I work for an agency where we deal with the public and we have to implement decisions that have some technological implications for people that they don't get. And we don't have anything to do with the DDTV transition, but that's an example of one where regulatory bodies have to sell to the public a massive change. So my question is, how do you get me and the rest of us who are in the 10% to move off of broadcast onto the internet, and how do we get that for free since we get broadcast for free? And if we aren't going to get it for free, how do you sell the extra money? I mean, having to pay for it.
Right. Okay. No, that's a fair question, and I'm not unsympathetic either because we rely on rabbit ears alone at home, mainly to keep the kids off television, and
so the de-incentive.
So instead, they're on Facebook all the time. And I also co-directed this Digital Future Initiative for PBS, which was all about the television future. And that's the thing is about the future. Actually, our original proposal for the DTV transition, I think, probably answers your question. We originally went. The DTV transition we're going through now with the hard deadline, February 17th, to turn off analog transmissions forever, that was originally, John McCain's bill. And when we went to him originally, the proposal was, let's get these guys off the air completely by having the auction, this auction we had earlier this year, have an auction a year ahead of the deadline and earmark the first $3 billion to buy people who rely on over-the-air, either a cable set-top box or a satellite dish, and so everybody could, the government would basically pay for you to get on to these systems, and then partly too, we went around and tried to convince the cable and DBS companies that that they should give people their local kind of lifeline service free. In other words, there's no marginal cost for them to turn on access to just your local TV stations that you get over the air. And then once they have these people, at government expense, they have these people connected to their networks, then they can upgrade them to premium service or sell them internet access or something else. And that just proved to be a bridge too far in terms of I think it just blew the minds of the cable and satellite guys. McCain wouldn't go for it unless they agreed to come out publicly ahead of him. So we ended up with what we got, which was the converter box coupons to turn your analog TV into a digital receiver. But I think we just need to revisit this again. And the other thing that's coming along, is you should be able to view these stations over the internet. Yeah. So if you have, once you have a high enough broadband penetration, that's yet another option. And so I think between streaming on the internet and some subsidy perhaps for a cable or satellite connection, we ought to just set a time a few years from now where, like this DTV transition, we do it again.
I just want to add one little thing: is there are some proposals out there to actually have free wireless internet access. So if you actually can couple what you're trying to do by streaming over the internet and coupling with some free access lifeline services, you may actually have an interesting solution to that problem.
And ironically, too, one last thing is that one thing the TV white space does, which is why Dell and Philips, these consumer device makers, have been such strong advocates, is it's going to allow you to essentially much more easily stream content from your computer to your TV set. So TVs in the very near future will all have Wi-Fi built in.
I'm Heather Hudson from the University of San Francisco, and my question was actually quite similar to Helen's, but I'll try to take a different angle on it because I had some other questions as well. But it seemed to me the most interesting word in your response just then was just. Just take everyone off when everyone has access to broadband. I mean, that's a big just. But is there a positive way to turn that to a goal for a new administration, which I know your foundation is also working on, as part of the, yes, we need broadband everywhere strategy first, and that does involve the states. I mean, you got to get Helen and people on board for that because I don't think we'll see a federal initiative. So that's one question. Do you see this as a driver toward the unmet targets of broadband? That still raises the issue of paying versus so-called free. But I also had a question for the last speaker on this because I understood you to say, although you were working in DoD spectrum, that spectrum, when you get these radios working properly, really wouldn't be a problem. So does that mean that we really don't need the TV spectrum in order to do most of these things? Or was that just spectrum's not a problem in the different parameters and less used or less controversial for consumers, DoD spectrum?
This is on. The DoD would like to have 10 or 100 times the spectrum they have now. So for them, this is a way to avoid coming to you and trying to take all your spectrum from you. So I think some people, this will solve their spectrum problems for the short term.
But can you tweak those, as you said, interference levels and drop levels so they work on radios in the TV spectrum and we don't have to give up TV, or is that really...
No, I think this whole white space that's coming out, unlicensed white space, is allowing you to keep your TV and let other people use the holes. So that's exactly what's being proposed now, is make better use of what...
Right.
Yeah, right now the
Okay,
TV...
so
You'll never know this is going on.
So then why are you saying get off TV and how do you get to the just?
Well, no, that was just, I was saying as a future step, in terms of more efficient spectrum use. I mean, right now, everything we're referring to as TV white space are actually the vacant channels, the unassigned channels, the guard bands between the old analog channels. So, in other words, the typical TV market in the United States, local TV market, has seven or eight full power stations, but there's 49, even after the auctions this year, there's 49 channels still exclusively available for digital television, even though, there's only typically 7. It ranges from, say, 4 or 5 in Alaska to 18 maybe in New York or LA. So no matter what market you're in, there's a lot of just empty channels. Now in the future, you get down below 10% of people watching over the air, it would be great to find some alternative way to view television so that then the rest of those channels, not only is the rest of those channels freed up for broadband, but it means that all today's white space can be used at higher power levels, can be used in a more robust way. So that was the point.
I want to add one thing. Your question might also be driving toward TV because of what's called a big stick architecture. basically does not allow frequency reuse. So you know why cellular systems only need a few megahertz of bandwidth, right? So therefore, if you go to a cellular type architecture or some kind of architecture like that for TV, you also open up a lot of spaces associated with that also.
Don't need those big towers. Okay, I'll let somebody else ask.
Yeah. Yeah, and we'll just make these the last couple questions because we have to go. We have to get Tim Wu up here to speak.
I'm cutting into my own time. My question is for Mark, and I'm a believer and a fan of everything that's happening in DSA and white spaces. But I just, having been in the industry for not that long, but long enough to know that there's been a lot of sort of promising broadband technologies or radio technologies that then turn out to have more problems than people thought at first. I wonder if you would say, leaving all the policy and politics out of it, what you think are the greatest technical challenges for DSA really taking off, if they're there, and all. Is it like, do you feel really confident in front of this room saying, yeah, what are the greatest technical challenges facing you?
I used to be a program manager at DARPA before Paul, and I tried to start the program, and the director said, "What are the technical challenges?" The director asked, "What are the technical challenges for DSA?" I came back and I had a kind of a crummy answer, and he says, there are no challenges. And I iterated them 2 or 3 times, and then I left DARPA because there really are no hard technical challenges to do this. The biggest issue is the cost of the radio to be multi-band. We're just doing automated what people would have done manually. Manually, spectrum engineers do all these things to squeeze people in. We're just automating them. So this is not technically that, it's hard, but there's no breakthroughs required.
Well, what I heard, just a quick thing, what I heard at DISPAN, I was with these guys last week in Chicago for all these engineers, and I didn't understand a lot of what I heard, but one thing I did understand was that it seemed the biggest challenge was a business model challenge. That it wasn't clear. In fact, there was a guy from Vanu, this is Bose's son, Vanu Bose, who has this Vanu radio company, and saying that he had a hard time seeing where the business model was, unless actually as more new companies come along, and there's no new spectrum to assign, they decide to create pools of spectrum and dynamically share that. But so I don't know if you guys have a comment on that, but it seemed to be more of a business model than a technical issue.
Tim Pozar, just geek. I have one technical concern, is that you're limited by Shannon's theory still. And with more and more demand of bandwidth out there, Google's, YouTube, things like that, how are you going to address that with the 18 megahertz of spectrum that you may have in New York City?
But in New York City, only 10% of the spectrum is being used. There's over 100 megahertz of, I hate to pick on DoD, but the DoD has telemetry spectrum for Edwards Air Force Base. They don't use it in New York City. There's 100 megahertz sitting there. We didn't measure any signals there.
That was the yellow.
Because that's being used at Edwards Air Force Base,
right.
But there's no technology that
Okay, so you got 100 megahertz. Well, but you still have people out there that are trying to download, via Hulu, and these other high-demand bandwidth sites.
Well, eventually you just have to put more cell towers in. You can scale wireless endlessly by having 2-meter cell
dimensions. So we're looking at picocell.
Wireless will scale to any capacity by putting more cells in.
Well, but if you also look at the amount of spectrum that's out there, okay, you just look at 3 gigahertz, okay, of spectrum, and you'd actually take 1 bit per second per hertz, right? And then you take it across maybe that a one cell site will satisfy 10,000 people. You can start doing the division. If you do it actually correctly, you can actually probably have many megabytes per person available. The question is how to get the sharing to be just right and actually stitching all together. But from the highest level, right, you can actually do a Gedanken experiment and say the bandwidth is there. The question is how to get access to the spectrum and stitch it all together.
Well, I'd love to hear that discussed sometime.
Okay.
All right. Well, we should move on to our second group. Thank you, Paul and Mark.